This is a video for AQA Further Pure, Complex Numbers 5, Complex Roots, 5.4, Solving Equations. We've already seen how to solve equations like z to the n equals 1 and z to the n equals w, where w is any complex number. Z to the n equals 1, we talked about the nth roots of unity, and indeed here we talked about the nth roots of any complex number. However, sometimes we write this as something equals 0, so z to the n minus w equals 0 is another alternative that you'll see for this type of equation. It's important to remember that w can be any complex number, including wholly real numbers. So we could be talking about z to the n equals 6, for instance, or we could be talking about something like z to the n is equal to 5 plus 7i. Let's have a look at this example. We've got an equilateral triangle on the Argand diagram, and it's got a centre at 2 plus 3i and a vertex at 4 plus 3i. There's those points marked on the Argand diagram, and I've drawn a circle centred at 2 plus 3i which goes through 4 plus 3i. Because I've got an equilateral triangle, all the vertices of my equilateral triangle will lie somewhere on this circle. If I sketch in the triangle, I'm going to get something like this. And so my other two vertices are going to be here and here approximately. Well, how can I sort out an equation for those three vertices? Well, if this whole circle was centered around the origin, what we'd have is we'd have 3 points equally spaced around a circle around the origin. And that would suggest to me that we've got z cubed equals something. It's not centered around the origin, so I need to do a change of origin calculation to make this happen, this movement to this point here for the center. And to do that, it's just going to be z minus 2 plus 3i cubed. So these points are going to be the solution of this thing is equal to some number. And I don't know what that number is, I'll just call it w. What I do know is that 4 plus 3i is one solution. So if I plug 4 plus 3i into that equation, I should be able to find w. So 4 plus 3i minus 2 plus 3i all cubed is equal to w. Well, if we look at what's going on in the bracket, I've got 4 minus 2 is 2, and 3i take away 3i is nothing, so I've just got 2 inside the bracket, and that's q. So that would suggest that w is equal to 8. And so the equation I require then is my something cubed, z minus 2 plus 3i, all cubed, is equal to 8. So there's my original statement that it's going to be an equation in that form. I know about 4 plus 3i, so putting that in and working it through, I get a value for w of 8, and so the vertices are the solutions of this here. We're going to solve this by essentially treating it as z cubed equals 8 to start with, and then when we get each of the roots, we'll add the 2 plus 3i back in so that we get the final result. Let's have a look at how that's done. So there's my something cubed is equal to 8, but I've expressed this in mod argument form. The modulus is 8, and the argument, principal argument, is 0, but I can add multiples of 2 pi to that to give me multiple values when I divide down. So if I take the cube roots, obviously I just get this z minus 2 plus 3i is one of these things. And the one of those things is, well, that's been cube rooted. So that's a cube root for the modulus. And this thing has been divided by 3 because we divide the arguments by 3. We allow k to be 0, 1 or 2. We know there are only 3 roots for this. And in fact, if k takes a value above this, like 3 or 4, it will just wind round the circle and reproduce the same roots again. So 3 will produce the same root as 0, and 4 will produce the same root as 1, and so on. So here's what happens when we plug in the values of k. We just get 2. We get 2 cos 2 pi by 3 plus I sine pi by 3. So we get this minus 1 plus I root 3 here, and minus 1 minus I root 3. Now remember, these are the solutions as if this circle were centered at the origin. I've got to do my transformation of origin here, and that means that these need to be added in on the other side. So each of those will have a 2 plus 3i added to it. When you do that, you get final roots of z1, that's when k equals 0, is 4 plus 3i, and that equates to that point on the diagram. z2 is 1 plus 3 plus root 3i, and that equates to that point on the diagram. And z3 is 1 plus 3 minus root 3i, and that equates to that point on the diagram. So the technique for this question was to establish that the equation is essentially a cubic, but with a change of origin, to solve the cubic first of all, and then apply the change of origin at the end to produce the final results. That was the final video in this sequence, Complex Numbers 5, Complex Roots.